Good day, everyone. I hope this is a good time of year for everybody. The topic that I'd like to talk about today is how solar radiation affects Grand Canyon, both the life in it and the environment there, perhaps even the geomorphology. So I titled this talk, "Light Breaks Where No Sun Shines." It's a phrase out of a very famous poem by Dylan Thomas, one of our most renowned poets of the 20th century. And the topic is really about how sunlight comes into this large, deep canyon. So the history of the museum's research in Grand Canyon goes back almost a century, starting with Walter McDougall and some of the early naturalists and botanists around the region. Eddie McKee, of course, came to Grand Canyon in 1929, I think, and put together some of the first species lists. Steve Crothers, former curator of biology here at M&A, is a prominent architect of Colorado River management, as well as a great investigator of the natural history of that landscape. To put us back in context here, Grand Canyon is about halfway through the course of the Colorado River. That river is 1,400 miles long. Grand Canyon falls in the middle part of it before the river turns abruptly south, but it's a very circuitous portion of the river and has some very prominent tributaries coming into it, the Little Colorado River, Kanab Creek, Paria River, etc. The landscape is complicated because Grand Canyon lies at the boundary of two great geologic provinces, the Colorado Plateau portion of the Rocky Mountain province to the north, and the very vast Great Basin province that lies, Basin Range province that lies to the south and to the west of Grand Canyon. So that boundary line is just south of Flagstaff along the Muggione Rim, but the contact between those two geologic provinces really, in a way, extends all the way up through Grand Canyon. So this is a mega ecotone. It's a mixing zone for species over time. There are four major biomes in the region across these two geologic provinces. The elevation range is pretty tremendous, 3.5 kilometers of elevation range. And it's, as I said, it's quite a diverse landscape. Macroecotonal biodiversity with 2,500 plant species at least 500 vertebrate species, and probably more than 20,000 macroinvertebrate species, although we don't know quite how many insect species we have in Grand Canyon yet. I've got about 10,000 documented, but it's just a start. Now, the configuration of the canyon is also quite important here. As I said, it's a very circuitous route that the river has developed through the landscape over time, with sections that run to the south, sections that run to the west, and then very oddly, a couple of major sections that run to the northwest, very much against the laws of logic there. The Colorado River cuts up into the Colorado Plateau, the East Kaibab monocline, going against kind of the grain there. And then when the river hits Diamond Creek, it again turns abruptly to the northwest rather than flowing out Diamond Creek, which would be perhaps another way the river could have gotten out of the Colorado Plateau. At any rate, these twists and turns in the canyon and the depth of the canyon, which is in many places, closing in on 2 kilometers, is enough to create many different situations that block the sunlight moving into it. Okay, so we're talking about sunlight here because it affects weather and climate, and those effects vary across space. And Grand Canyon is a great place to explore all those topics. Sunlight, of course, is the promoter of photosynthesis and productivity, productivity being the rate of plants' ability to fix carbon per unit area over time. So productivity varies tremendously across the elevation and water gradient that we have in Grand Canyon. We'll talk a little bit about how to measure sunlight and what that means to us. But then we also want to talk about how sunlight might affect the geomorphology of Grand Canyon, its ecosystem functions, the kind of species that can live in this often light-limited environment, and then the consequences of this variation, solar radiation, both in terrestrial and aquatic habitats, and perhaps to some extent its role in climate change as well. First, what is sunlight? Any good physicist will tell you that sunlight is a bunch of photons that are massless bosons arriving in waves at the speed of light. We've probably all heard that there's variability in the wavelength of those lights. We have infrared visible and ultraviolet lights, as well as other forms of electromagnetic radiation coming to us from the sun. And the sunlight at your window there departed from the sun about 8 minutes and 19 seconds ago, and it's just arriving now. So there is a bit of a lag in terms of the arrival of light from the sun here, but not too much because we're pretty close. Now, sunlight coming into the Earth is filtered by a number of different processes, from molecular to kind of macro atmospheric particles, vapor, clouds, and other aerosols and whatnot. The angle of the sun changes daily, of course, and seasonally, and that's related to the Earth's rotation and tilt. And so all of these factors influence the intensity of the atmosphere the sunlight has to pass through and the distance through the atmosphere that it has to pass through. And then physicists get excited about why the sky is blue, explaining it through Rayleigh-Raman and my theory, scattering of light off of the largely nitrogen-based atmosphere that we've got. This gives us, in general, a solar constant, which is the arrival of photons and translation of that light into energy at the Earth's surface of about 1,361 watts per meter square. But of course, the reception of the Earth varies in terms of the kind of landscape that that sunlight is hitting. Why are these processes important? Well, this gives us warming, a critical kind of part of our existence on Earth here. It provides us with photosynthetic products. It shapes our climate, it shapes wind, and of course, shapes our ability to see. So all those things play a great role in our appreciation of Grand Canyon and our understanding of the Earth around us. Looking at the atmosphere, the sunlight has to pass through. Troposphere, stratosphere, mesosphere, thermosphere, going up to about 95 kilometers in height above the Earth is the extent of our atmosphere. Note that about 50% of the Earth's atmosphere is below 10,000 feet elevation. So 50% of the mass of the atmosphere occurs in this lower 10,000 feet, and the rest of the 50% of the atmosphere takes place over this incredible reach up into the thermosphere. Things in scale here: Mount Everest at 30,000+ feet, Mariana Trench at about 35,000 feet, Grand Canyon, very impressive feature, but not as deep as some other canyons on Earth, and extending into the Earth maybe 1.5 kilometers or so. San Francisco Peaks, again, being a very impressive range for us, but nothing compared to Mount Everest. But nonetheless, we have a good elevation range here, and elevation, as we'll see in our talk here, matters a lot to the reception of solar radiation. Now, part of this too is that the Earth is rotating seasonally about 23.5 degrees, and so that rotation means that in the wintertime the sun is having to pass through more atmosphere to reach us, and importantly, if the angle of the slope in the Grand Canyon is more than 23.5 degrees, that slope will be in shade during the winter. The axis of rotation of the Earth is quite important to our story, and that's really a function of the latitude that we exist at here, about 35 degrees north latitude. So, as I said, sunlight is an important ingredient of the process of photosynthesis. Photosynthesis is about CO2 and water being influenced by light in chloroplasts, which are actually ancient parasites living in plant cells that are able to transform with these ingredients the energy of light into plant starch and oxygen and water, with oxygen and water as waste products. So why is this important? This process of photosynthesis, light striking plant photosynthetic plant material, has provided us with a free oxygen atmosphere for the last couple billion years. Kind of a big deal. It's given us plant life and all the foods that we are derived from that, as well as provided us with our fossil fuel sources. So photosynthesis has been a phenomenally important process on Earth here. And photosynthesis is a really complicated process. It involves several different pigments and different compounds of chlorophyll in the chloroplast that do this transformation. And not all wavelengths of light are equally useful to chlorophyll. So the greens greens and yellows are important to light, and also moving out into the reds, not so much in the blues to a lesser extent. So the wavelengths of light coming to us from the sun are filtered by the atmosphere, and they provide us with a suite of wavelengths that plant life is specifically adapted to. It has been adapted to for the last, close to 2 billion years or so, maybe more. So through evolutionary time, these chloroplasts have become very attuned to the kind of light that they receive. And different species of plants, of course, very attuned to whether they're growing in shade, whether they're growing in direct sunlight, whether they're, in a situation in which they're facing variation in light, seasonal or even sometimes climatic variation in life. So plant life is very, very specifically adapted to variation in sunlight and the wave intensities that can come to us. Here's a map of photosynthesis of the world, showing that the oceans are kind of low in their chlorophyll A production, but that there's plenty of highly productive tropical landscapes that are pumping out a lot of photosynthetic product. Now, the issue of net primary productivity is based on an annual reception of sunlight at the surface of the earth, producing plant starch. And in our desert landscapes here, the cliff walls of Grand Canyon, especially on south-facing slopes, that production may be as low as 1 gram per meter square per year. So very, very tiny amount of productivity, can't support much other life because it's just so little. But when we get especially into kind of warm springs, such as Montezuma Well or some other warm water springs that have a lot of high solar radiation intensity coming into them, those are places where we can have orders of magnitude higher primary productivity. So that productivity is a function of sunlight coming in, but it can be absolutely enormous in these highly productive aquatic environments, shallow aquatic environments, especially those that aren't changing very much through the course of the year. And then various portions of the landscape are actually pretty productive. Deserts, not so much, but the Amazon basin and portions of the northern forest can be quite productive. Okay, again, we're kind of wandering around here. A lot of different topics. Sunlight coming in. Sunlight's been coming in for a long time. We know that. But Grand Canyon is a landscape that's changed a lot through time. We've had 3 major orogenies that have influenced the shape of the canyon, and the most distant one was a severe orogeny. That was a mountain building event where the Earth's crust was being pushed together, compressional event. Then the Laramide orogeny, beginning about 80 million years or so, again contorting the Earth's surface, some compression going on there. And most recently, in the last 22 million years or so, the Basin and Range province, that compressional process has reversed. And now we have this landscape off to the west of Grand Canyon and to the south, is where the Earth's crust is pulling apart in what's called extension. So these orogenies have really shaped the structure of faults and fractures, probably shaped the course of rivers prior to Grand Canyon, and some of which we apparently have some evidence of still in Grand Canyon. During the Miocene time, say 15 million years or so ago, at the beginning of the Basin and Range orogeny, that's when our landscape began to come into focus. This could be the time in which some of these ghost canyons that Carl Karlstrom and Wayne Rainey have been talking about became integrated into the modern course of the Colorado River. But that process began back probably in Miocene times mostly. Most of our biota, all our recognizable biota and flora and fauna come from that time frame as well. So the evolution of horses and camels and rhinoceros and the separation of bears and dogs, the derivation of cats from that carnivore lineage as well. Those evolutionary events are all kind of early to mid-Miocene and have given us the flora and fauna that we recognize today. During Pliocene times, between about 8 and 2.5 million years ago or so, the landscape became more desertified as the Sierra Nevadas range rose up and blocked the eastward flow of moist air from the Pacific Ocean. During Pleistocene times, cooler, at least more humid climate. Lava flows pouring into Grand Canyon created huge dams. We had other enormous lakes in the western U.S., such as Great Salt Lake, and the glacial phase climate was quite a bit different than today's climate, which is is really the result of post-Pleistocene desertification, kind of remarkable life zone shifts. The life zones we have on the San Francisco peaks moving upslope 3,000 feet in the last 12,000 years, probably mostly between 12,000 and 8,000 years ago, and then the loss of these Pleistocene megafauna that roamed the landscape, possibly due to the arrival of humans here, or to improvement in their hunting techniques, and then climate change, modern climate change, very much the result of human impacts on the landscape. So Grand Canyon has really been a land of change, both in terms of the geomorphology of the landscape and due to climate. That has given us this kind of picture of how the landscape has changed here during interglacial times, warmer, dry times, like all of human history has taken place in this last 10 or 12,000 years here. During those times of dry conditions, has been a northward and upslope colonization of the landscape. The glaciers receded, and that allowed for more space. The probably perennial ice fields that existed here in the 15,000 years ago turned into our meadows here in northern Arizona. During glacial advances, which really dominate the climate scene here over the last couple million years, and with glaciers going back all the way to the time of the Cambrian, 500 million years ago, during those times, southward and downslope shifts happened, where the fauna and flora were displaced from the upper elevations where snow and ice formed and pushed down into the deserts. So this is the kind of changing landscape that we've been living in over here, and what we have here now is very much a reflection of that process. We talked about Grand Canyon as being a large, deep canyon. It has a corridor that allows for a through flow of genes and propagules and organisms. It can have barrier and filter effects, the kaibab squirrel, for example, and it can have refugia within it. These refugia are part of the topic today, in that little places in the canyon that are on, say, south-facing, or on the south rim, which is a north-facing slope, might have a very different flora and fauna than those that are located at a similar elevation, but on a south-facing slope across the canyon. So we're talking about aspect refugia. Aspect is the angle at which a slope faces, and these aspect refugia are particularly interesting places to look at in Grand Canyon. North-facing slopes at low elevations host Canadian plant species. South-facing slopes even at high elevations, such as the south face of Mount Eldon here right out of town, support things like century plants and tree species that really reach their northern range limit in these south-facing situations. Also, we have microhabitats, like caves, but particularly springs that have strong aspect effects and can really shape the persistence of many populations here. Now, I didn't much mention about the shift in the configuration of the canyon has moved from east to west, but we have something called the Muav Gorge about halfway through Grand Canyon that isolates an eastern basin from the western basin. And an eastern basin seems to have more severe aspect effects than happens in the western basin, which is more connected to the deserts to the west. These are all topics I talked about in a paper. If anybody's interested in that paper, I'm happy to send you a link to it. It's on the web for free. So, but it's about the biogeography of Grand Canyon. Okay, so here we have Grand Canyon, a large, deep canyon with slope angles varying on the two sides of the river. A much more gradual slope on the north side. If any of you have hiked from the south rim to the north rim, you go down very steeply down one of the trails to the river there, and then it's a much more gradual climb to get out to north side. And so we've got these changes in the slopes of the canyon, and sunlight coming in, varying on the basis of the time of year, rocking back and forth. But the slopes of the south rim, which face north, their angle is much too great for sunlight to be able to reach them. So north-facing slopes, even in the summer months in Grand Canyon, can be shady. can be shady. Whereas slopes on the north side facing south are very, very typically hit by the sun. Depending on the time of day, the sun angle comes in, and whether the shade develops, it develops from the bottom up during the afternoon hours, eventually reaching the rim. Any kind of microhabitat, like a spring that comes out here, will be subject to that solar radiation budget in a very fixed way. So one of the kind of very cool things about Grand Canyon is not only is it geologically spectacular, but it has all this variation in solar radiation arrival, which is every bit as important to the ecology of the canyon as the geology is. Okay, pretty famous drawing of the life zones of the San Francisco peaks. Grand Canyon, Seahart-Merriam, of course, traveled into Grand Canyon to the Painted Desert off to the east of us and across the peaks here to identify these zones of vegetation. Now, in this fairly famous drawing, it looks like the role of aspect here. This is a kind of a view from the San Francisco peaks looking from the east. So the south-facing slopes are on the left side, north-facing slopes are on the right side. And he indicated that he thought that aspect effects were more severe as you move from the increase in severity as you move from the south-facing slopes to the north-facing slopes. Is that true? Well, we don't actually know. Nobody's bothered to measure this on the peaks. I can't see much of a pattern, a strong difference there. But certainly it's true that the south-facing slopes do host a hotter, drier, and different vegetation assemblage. But whether or not the angle changes by life zone is, I think, quite a bit up in the air. That really deserves some more careful examination. Again, the landscape that we're dealing in here, Grand Canyon, the elevation ranges from about 360 meters on the surface of Lake Mead, 1,100 feet or so, going up to the top of the peaks at 3,850 meters. So a tremendous elevation range here, and that gives us not only the story of aspect effects to look at, but also the role of aspect across elevation. Again, that needs some more attention here, but here we have one hypothesis about how Seahart-Merriam thought it looked 130 years ago. Now, so how do we actually get any measurements out of this whole story? Well, there are basically kind of three main ways. We can take a landscape model of the Earth, put it into a geographic information systems analysis, and do some modeling of integrating sun angle over the course of the day and over the course of the seasons and years, and develop a stacked map indicating how to evaluate, say, photosynthesis and solar energy across the year. And we're trying to measure kind of light ranges, visible light ranges from 0.4 to 0.7 micrometers of radiation over this range here. This is the visible light range, the range that is really responsible for photosynthesis. So that's one way to do it. You can. The problem with that is these are not very high resolution landscape maps, usually 30 meter DEM. We do have 10 meter DEM, but it turns out 10 meter DEMs, desert elevation models, are no more accurate than the 30 meters when it comes to, what the effect of a prominent rock or outcrop on the rim is that might cast a shadow that's quite large down on the floor of the canyon. We can undertake point measurements by dragging around a pyranometer, putting it at a point, measuring it, leaving it there for a year, recording on a little laptop, and that will measure the actual solar radiation flux density in watts per meter square. So you get a very accurate measurement for a single point here. You get kind of an inaccurate measurement from GIS of a whole landscape. And but this takes putting one of these devices that costs a couple $1,000 with all the equipment associated with it in a point for a year, during which time it's undoubtedly going to get vandalized. So that's kind of a tough way to go. What I've been using is a point-based device called the Solar Pathfinder. It costs about $250, and it's a very cool little tool. It gives you a point-based analysis of solar radiation, but you can get a measurement within 1 minute. So it's kind of a very rapid way of getting measurements. You can take a lot of measurements in a hurry. Now, this is a device very ingeniously created by a couple live in Arkansas, and they provide a template for each latitude. This is the latitude we use here, 31 to 37. That's most of Arizona. And the solar, this template is based on the months of the year, going from the low light month here in the Northern Hemisphere of December down to the highlight month in June. So 12 months there. And the vertical lines are the solar time of day. These little tiny numbers are the percent of daily sunlight that comes in each half hour of the day. So each line adds up to 100%. And this gives you if you adjust for declination and if you adjusted for latitude, it gives you the average monthly sunrise and sunset time for every month of the year. And you can take this information, integrate it, and develop a potential solar energy budget for the site. Now, this doesn't include cloud cover, aerosols, or anything like that, but with some math, you can get around that. And so this is a very easy device. We can backpack with it and get it all around the landscape. And you put a reflective dome over it, and where the sunlight reaches the edge, sunrise happens on the left side here. Sunrise at this point was blocked by tree life, but no canyon walls. And on the sunset side, the right side of this thing, you see a very clear line of when the sun set against the template down below it. So these devices are accurate, moderately accurate. Like I say, you get the average sunrise and sunset time per month, and from that you can get a sense of the potential direct sunlight. Couldn't probably use this too well in the tropics with a lot of cloud forests, or in landscapes with just completely forested. But here in the Southwest, this is a really great tool for understanding the solar radiation budget. So let's look at some of the results and consequences of solar radiation here in Grand Canyon. And it is so hot out here that maybe the cacti do have to wear sun protection some of the time. I don't know, but we can see the kind of variation in solar radiation budget effects across spatial scales here, looking at species, at local and microsite conditions, at kind of larger landscapes, synoptic reach-based analyses, and perhaps at whole landscape. And we also look at an interplanetary, can we develop interplanetary solar radiation questions here too? These are, we'll chew on this a little bit. So we have plants in our landscape that really don't like direct sunlight. They really like reflected sun off of cliff faces. And helleborine orchid on the left side here, and maidenhair fern are two of quite a few plants that just can't stand direct sunlight. They really love shade. And so their physiology is adapted to receiving only shade in kind of canyon settings may amount to not more than about 10 or 15% of the solar intensity of direct sunlight. So these are plants that can only handle up to 10, 15, 20% of direct sunlight. Otherwise, they just don't have the capacity, physiological capacity to be able to transpire at levels above that, and they will and die or desiccate. So these are important species, as it turns out, when we come into hanging garden habitats. These are habitats that are the Four Corners area and Grand Canyon are renowned for the number and diversity of hanging gardens that exist. Hanging gardens can face north, they can face south, no matter what. This is one I visited a month or so ago. That's a south-facing hanging garden, but it was overhung by almost 15 meters, and therefore the overhang permanently shaded the wet back wall. The wet back wall is a habitat that we know only a little bit about from botanically, but this is a spongy, moss-covered, probably many species of mosses and other microplants living in this seep dripping wall. There are invertebrates that live inside those moss beds, and it's a really unique habitat. Again, we know about it mostly from the plant life on it, not from much else about it, but it's a permanently wet back wall feature habitat. Okay, so at this spring, I was kind of amazed to see in that this portion here is north facing, this portion over here is south facing. The highly shaded portion supported Eastwood's monkey flower, And so that's the only place it occurred at this site. And in the south-facing slopes that got full sunlight, Mimulus cardinalis, the crimson monkey flower, was the dominant. The Eastwoods monkey flower did not occur anywhere over here, and the cardinal monkey flower didn't occur anywhere on the north-facing, the deeply shaded sites here. Kind of a cool little example. Other hanging gardens, such as Cliff Spring in Grand Canyon National Park. This is, in addition to many things, one of the best birding spots in May and June in the whole park. This is a hanging garden that supports a population of rare primula, and the primula lives on the wall surface here in the dripping back wall. It probably is able to stay there because there are a number of tetragnathed spiders that build their webs here. My friend Paul Dayton noted that it's probably the seeds catching the spider webs adhere to the wall and allow this population of plants to have existed here for more than 50 years. It was discovered more than 50 years ago there, and it's persisting, even though these are probably biennial plants. Anyway, so in doing a solar pathfinder analysis at this site, placing the solar pathfinder in the floor here, we see that this is a site that it's at high elevation, 7,000, 8,000 feet. It receives full sunlight during the winter months, and it's fully shaded in the summer months. So it's a great place, huh? This is high elevation, shading in the summer, full sunlight in the winter. This would be probably a good place to look for archaeological remains as well. That unique environment allows this plant, primula, which is again one of these species that really requires shading to live in here and live its life cycle during the shaded summer months. And during the winter, of course, it's cold enough that it's deciduous, it's died back. So it's able to persist that way. In an analogous site, this is an east-facing spring called Vasey's Paradise, mile 32 in Grand Canyon. And its solar radiation budget is such that it's east-facing, so it receives direct sunlight during the summer months, but nothing at all. It's fully shaded in the winter. So, but one thing that's interesting here is that all the sunlight that it receives shows up in the morning. The afternoons, the landscape is shaded, so the site is protected from the harsh late afternoon rays that are so drive the landscape out. And because of that solar energy relationship here at this site, it allows the snail formerly known as the Kanab amber snail, it was an endangered species, now been renamed the Niobrara snail after finding that it's related to this common species to the north. This Niobrara snail is able to persist here, even though it's a high elevation, high latitude species. This is the southern, about the southernmost population of this snail that we know of, but it's being able to persist here because of the solar radiation budget. So we've looked at a species that require certain light settings, points in the landscape that serve as refugia. Now let's look at kind of a larger landscape view. And this is famous gooseneck there at Point Hansborough in Grand Canyon, mile 40 at Buck Farm, coming down to mile 47 at Saddle Canyon. This is among, if not the largest, the most deeply incised river meander in the world. I don't think anybody's recognized that as a part of its story here, but it's also a wonderful place to be able to look at south-facing versus north-facing slopes. You got the same geology, Moab-Cambrian formation all along this whole gooseneck. The left side of the river is south-facing when you're on the north side of this, and that side changes. It becomes north-facing when you're on the south side of the meander. Similarly, the same reverse situation exists for north-facing slopes. So the north-facing slopes here support a typical Sonoran desert vegetation: mesquite, acacia, brittle bush, number of cacti. But interestingly, no grass, virtually no grass whatsoever on a pristine site that hasn't really ever been grazed. The north-facing slopes support Great Basin desert vegetation, including things like buffalo berry and juniper trees and hackberry. So the river is about 100 meters across there, but you have got two different biomes living on the two different sides of the river because of aspect. I put in thermistors across this transect to see what was happening. The river, of course, modified the temperatures and climate conditions right down near the water. But as you moved up onto the slopes, living on the north-facing slope was the equivalent of living at 1,500 feet higher, 500 meters higher in elevation than on the south slope because of the aspect effects there. So this is a really wonderful place to look at aspect impacts on vegetation, and also there's virtually no species in common on the two slopes. One species of Mormon tea and one cactus species occur on both sides, but otherwise very little overlap in the vegetation whatsoever. And also very few mammals or even insect life similar. So this is really a remarkable place to be able to study this whole topic of solar radiation. Another place in Grand Canyon that's particularly interesting to look at is downstream from Kanab Creek. This is the river anticline section. Again, many places where you have north versus south facing differences on the two sides of the river. Here, the Moab Gorge is the separation zone between the eastern basin and the western basin, and it's a very steep, narrow canyon here. It's so steep that even during the summer months, sunlight may not penetrate to the very floor of the canyon very much, especially even on south-facing slopes. And during the winter months, it's just locked in. It's quite cold and shaded. So no direct sunlight in there, as anybody who's done a wintertime river trip knows. So interestingly, one of our grasses in Grand Canyon that occurs pretty much only on north-facing slopes at low elevations is this James Guyetta grass, Pleurophis hemesii. And this is a species that in this section, because of the very, very steep, narrow depth of the canyon there, occurs even on south-facing slopes at low elevations. It probably can occur at middle elevations, not that anybody's been able to climb up through that mess to get to see what its upper elevation limit is here. But this portion of the river corridor, even on south-facing slopes, you find this species of grass. But again, you get these little clues about how much of a role solar radiation plays in the distribution of even pretty common species. So I put together a kind of a theoretical large steep canyon here, and this is a river. It could be flowing either direction, doesn't matter. The mainstream are these wider bars. Tributaries coming in are the narrow bars. So portions of the mainstream that are flowing east-west receive, sun is rising and setting and flooding that portion of the canyon with light. But there is an issue of how high the walls are. If the walls are pretty steep and high as they are in Grand Canyon, a shorter reach that's flowing east-west will have a cooler environment. It won't receive as much sunlight as the longer reaches. We could call it a solar fetch, I suppose, and not having a term for that kind of concept. Sections of the river that are flowing either north or south they do receive sunlight if the sun angle is high enough. They'll receive sunlight in the summertime, but during the winter, they're going to be locked in shade. Tributaries coming into the canyon, if they're coming in from the south, they can bring in a great deal of sunlight, even in shaded regions. However, if they're coming in from the north, if they're coming in from, say, the west, they'll bring in less light into this canyon environment. What that means is that the area around these tributary mouths will very much reflect the solar energy budget around them. Productivity, both in the river and on the riparian zone, will be influenced by the direction of that tributary flows into the canyon. So all these light intensity issues, they decrease with latitude. The farther north you go, the more severe, the lower the sun angle is in the summer months, and so latitude plays a big role in solar intensity. Elevation plays a big role here because harder to get a super deep canyon at higher elevation. Elevation does, though, reduce the amount of interference in that sunlight arrival. Atmosphere is thinner at higher elevations. But then, of course, canyon depth can also shape this entire story, with some reaches being so deep that they actually never receive perhaps any direct sunlight whatsoever. All right, and dragging the solar pathfinder around Grand Canyon, these are the results here, broken into the geomorphic reaches that Schmidt and Graf defined in 1990, 13 reaches. Those that are in wide sections of the canyon, like the Glen Canyon, the Permian Reach, the Furnace Flats Reach, the well-named Furnace Flats Reach. These are wide reaches. Many of them flow. Many of the directions are either receiving quite a bit of sunlight. The east-flowing Lower Granite Gorge, for example, all receive a fair amount of sunlight. The Muav Gorge, that one we were just talking about there, really the solar radiation intensity there is only reaches about half of the other reaches of the canyon. The amount of sunlight coming into that reach, only about half of that's available if you were up on the rims here, where 100% would be available. So the reaches of the river, the geomorphology, the shape and the direction that the canyon flows there is influencing how much light comes into those portions of the river. Now, to expand this argument a little bit to landscape evolution, perhaps, the Colorado River transports sediment out of the Colorado River basin, and it's done a really good job of doing that. I think 75,000 cubic miles of the Earth's crust has been transported by the river off the surface of the Colorado Plateau over the last 50 million years. But what the real agent of erosion in this landscape is freezing and thawing. That the freezing and thawing creates small rockfall, large rockfall. Those particles eventually work their way down to the river corridor and get swept out. But freezing and thawing is what's responsible for the canyon being almost 20 miles wide at the lower reach, and whereas it's only a mile deep or less than a mile deep. So the width of the canyon is really a function of freezing and thawing in a pretty big way. But as we all know from doing our hike across Grand Canyon, south rim to north rim, the north side is this more gradual slope. So a question I have about this is, to what extent, if any, is the greater breadth of the north side, which is a south-facing slope, due to increased aspect derivative erosion? So freezing and thawing erosion is acting all the time. This is a south-facing kind of portion of the landscape. Is that what is in part responsible for the greater width of the north side of the river than the south side? It'd be a really wonderful master's thesis to do on that, looking at some complicated reach like the Tapeats Creek area. Anybody wants to work on that master's, please get a hold of me. I'm happy to talk about it more. So if is there evidence for aspect-driven erosion on Earth? There might be other applications of this. If Mars once had a wet climate, and it's some of the craters that developed there date to that time period, perhaps it could be that some of the craters on Mars are asymmetrical. They're not circular, but they might be slightly elongated. And this would take some very careful measurement to do. You have to know the age of the crater, and of course the latitude and elevation of the crater might have mattered then on Mars as well. So all those factors kind of come into focus. But the oldest craters should, if Mars did have a wet climate, could well have been. They could be asymmetrical. Might be something really to look at, and pretty fun to look at. Okay. Taking this to the last step, this is a look at temperature change on Earth over the last 70 million years, 65 million years since the time of the loss of the dinosaurs. And going from 65 million years ago, 65 and a half million years ago, with the impact that happened then to the modern times, you can see that the Earth's temperature has been cooling. And this is measured by using marine foraminifera and taking stable isotopes analyses out of those cores. But the pattern is pretty clear that the Earth's temperature has been cooling off over the past 65 million years, and part of it has to do with the opening of the Antarctic polar circulation system that now drives cold water around the Antarctic and up into both Pacific and the Atlantic. And so when that happened, then air temperatures cooled down. Now, of course, in climate change is bringing temperatures back up with potentially very problematic consequences for not only the natural world, but also for us humans. But this is the kind of the context in which we're looking at climate in our modern day. And so we can begin to look at air temperature change across the landscape. Of course, the Southwest is really prone to some of the highest changes in increases in air temperature. And the landscape that we are living in here may be somewhat less susceptible than, say, the Four Corners area and going up into North Nevada, going up into Utah and Colorado. Nonetheless, the refugia, the aspect refugia we're talking about, the north-facing slopes at low elevation in particular, are going to be ever more important in terms of preserving those species in the landscape. The high elevation south-facing sites are likely to expand in habitats, so species living in those habitats will be able to move more freely. Unfortunately, many of those species are non-native, so the consequences of that can be pretty dire. But it might be of very great significance to look at north-facing low elevation sites as long-term refugia for many of the species that are now rare in the Southwest. And preserving those sites as some kind of conservation approach might well be a good direction for us to think about. Okay, so in summary, we've seen that aspect effects on solar radiation budget is a very important, but it's largely been overlooked in large deep canyon ecology, LDC ecology. Aspect effects intensify with latitude and canyon depth and elevation. They are strongly influencing individual species distributions. The array of species we have in many situations, like these north-facing low elevation sites, and they do so by affecting the microclimate, and they're quite specific to the landscape. So these are fixed points in the landscape. Aspect effects may extend to landscape scale, as we saw in some of these larger reaches of Grand Canyon, these maybe solar fetch reaches and whatnot, also to whole sections of the geomorphic reaches of Grand Canyon, and perhaps even to the physiognomy, the shape of Grand Canyon in terms of differences in freeze thaw erosion on north versus south facing slopes. If there are any questions, happy to take those.
I'm curious, you clearly you show that the aspect ratio has a greater effect with latitude. Is there a place like at the equator where there is no effect of that?
Really good question. Yeah, would love to look at some of the canyons coming out of the west side of the Peruvian Andes. Those are some of the deepest canyons in the world, up to 14,000 feet deep, as opposed to the maximum 6,000-7,000 foot deep Grand Canyon. So in those situations, which are sitting right on the equator, you would expect the solar angle maybe to have less of an effect. And again, some of those canyons are so deep with so many kind of projections from the rims that it may be that the shading is also a very big deal there. Shallower canyons, probably much less of an effect. Once you get, especially once you get up to 45 degrees north latitude or south latitude, that's when these solar radiation impacts can be really, really severe. In Grand Canyon, we have the blessing of being able to study it in a landscape with all kinds of variation in slope angle in relation to the sun directions. So sun angles. So
sounds like you got a trip to Peru to take then.
Well, wouldn't it be wonderful to be funded to go to Peru and look at this? Yeah.
Absolutely. How much is there any effect from not just from the heat that the rocks there in the canyon hold and then release back out? I mean, how much of a thermal sink is there?
Yeah, really good question. So black rocks to red rocks are most they heat up more than lighter colored rocks. And so remember the floor of the canyon, schist, Precambrian brick red sediments. Those are sediments that really heat up enormously. I didn't talk about the adiabatic lapse rate in Grand Canyon. The adiabatic lapse rate is the rate of cooling of the air as you move up in elevation. And generally the pattern is 3 degrees Fahrenheit per 1,000 feet, 1 degree per 100 meters or so Celsius. So that adiabatic lapse rate is actually more intense in Grand Canyon than normal. You would expect there to be about with a 4,000 foot elevation change, you expect there to be a 12-degree temperature difference, but it's actually about twice that in Grand Canyon because those red and black rocks absorb more heat and re-radiate it back into the canyon environment. So Grand Canyon is the rock color can actually influence the heating of the canyon environment, making it kind of more dangerous to go hiking there in June and during the summer months.
Oh, fascinating.
And really appreciate everybody's time today. happy solstice. The light will be returning, and this is the season to be thinking about light.